Today we're going to be talking about some of the properties of exponents and logs. Hopefully in a previous course you've learned about the properties of exponents, and this exposure today will be relatively brief for that reason. But if you feel like you need further instruction on it, I highly encourage you to talk to your instructor and access your textbook as well. That will have lots and lots of examples of exponential properties. Really, the bulk of what we're going to be talking about today is logarithmic properties, because that is most likely the more new concept for you. So our first order of business is to review some of those exponential properties that you most likely saw during your intermediate algebra course, but you might not have used in a little while. And then we're going to be talking extensively about logarithmic properties. So for exponential properties, keep in mind that if I have two exponents of the same base multiplied by each other, that means that I end up adding those exponents. For example, if I have 2 squared times 2 to the third, that very literally means I have 2 copies of 2 times 3 more copies of 2 for 2 to the 5th power. And if you're ever forgetting any of these properties, I always recommend actually breaking out an example simple enough that you can write it out long form like this, like I just did here. And that'll remind you of the general rule that we do 2 plus 3 to find out our new exponent. And if you're going to do this, keep in mind, of course, that your bases have to be the same. If these had different bases, nothing would happen. Then for this next one, if we have two exponents of the same base being divided, that turns into subtraction. So for example, for 2 to the third power divided by 2 squared, that is very literally 3 copies of 2 being multiplied by each other over 2 copies of 2 being multiplied by each other. 2 divided by 2 makes 1. 2 divided by 2 makes 1. And you're just left with 2 to the first power, which was the same thing as 3 minus 2. If we have exponents of exponents, those get multiplied together. For example, if we have 2 squared to the third power, well, that's 2 copies of 2 multiplied by itself 3 times. So in total, we have 6 copies of 2 in this case for 2 to the 6th, which would have been the same thing as 2 times 3. We're also allowed, if we have a parentheses all to the exponent and the thing inside the parentheses is being multiplied, we can think of that exponent as being applied to each of these things separately. If, for example, I had 2 times x all squared, that would be the same thing as 2 times x times another copy of 2 times x, which could be rearranged as 2 times 2 times x by the associative property and the commutative property as well of multiplication. The 2 times 2 becomes 4. The x times x becomes x squared. Similarly, if we have things being divided, just a fraction, really, which, if I have a over b, that's the same thing as a times 1 over b. So really, this next rule isn't actually that different from rule 4. It just looks cosmetically different enough that we do tend to think of it differently. We can distribute, again, that exponent also to both of these as well. So for example, if I had x over 2 all being squared, that's the same thing as x over 2 times another x over 2. Multiply across the top, that's x times x is x squared. And then we have 2 squared on the bottom, which is the same as if I distributed it kind of separately to both. And working either way around might be more helpful depending on the context. Also remember that if we have a negative exponent, that becomes 1 over that exponent. For example, 2 to the negative 3 becomes 1 over 2 to the third power. So whenever we change a negative exponent, we make it the reciprocal instead, and then change that power to be positive. If we actually had a fraction that way, let's say we had 4 to the third all to the negative 2 power, then we would flip the fraction entirely and make this exponent positive. So that becomes 3 over 4 to the second power. So when you make it the reciprocal, that changes the sign on the exponent. So let's simplify a few exponential expressions and practice putting all these skills together. If you feel like intermediate algebra is fairly fresh in your mind, I encourage you to pause this video, try these problems yourselves, and then compare with me. If you feel like it's been long enough that you just want to look at some examples, that's completely fine too. Here, as my first step, I would go ahead and deal with this outside exponent. So I would think that 3 is applied to the x, and it's applied to the y. So this becomes an exponent of an exponent, means they multiply. So that'd be x to the negative third power, and that y is secretly to the first, so that's just y to the third power. Then I would go ahead and think, oh, if I have a negative exponent, that's the same thing as turning this base into its reciprocal, which is 1 over x, all to the positive power of that exponent, times y to the third. That 1 over x, that to the third power gets distributed to both of these. 1 to the third power is just 1. X to the third power is written as x cubed. And then most likely you would see this further simplified, that y over 3 is the same thing as y over 3 over 1. Multiply across the top, multiply across the bottom. 1 times y over 3 is y over 3. 1 times x over 3 is x over 3. It is possible that you did the same problem with fewer steps than I wrote out. If you still got the final answer and you have work that can be followed, that is completely fine. For this next problem, I would first deal with the fact that we have common bases where their exponents can be subtracted because they're being divided at the moment. So for the x's, that is x to the second divided by x to the first. That's secretly the exponent there. So we subtract those bases. That becomes 2 minus 1, which is just x. For the y's, we do a similar process. So that's y to the third divided by y to the fourth. That means I'm going to do 3 minus 4, which just gets us y to the negative 1. A negative exponent like that means he moves to the denominator, so that becomes x over y to the first. Now that y is to a positive exponent, which is just x over y. An alternative way you could have thought of this, since these numbers are small enough, is you could write this out long form and rederive those rules. So x squared is the same thing as x times x. Y to the third is the same thing as y being multiplied by itself 3 times. And then we've got an x and a y to the fourth. And then you would physically see I've got an x divided by x. That makes 1. I'm just left with 1x there on the numerator. Y divided by y makes 1. Another y divided by y makes 1. Another y divided by y makes 1. I'm still left with 1y in the denominator. That's an alternative way you could think about that. Just keep in mind that you can't use this long form way once these exponents become sufficiently large. So it's still good to know what the rules are. Go ahead and pause this video and try this next one. Just take it one step at a time. Don't try to do all the steps at once. Here there's more than one correct answer on what you might pick to be your first step. I personally go ahead and bring this exponent to each and every term here. And what you want to keep in mind is there are really 4 terms here. Sometimes people see these variables and they only distribute the exponent to the variables. Keep in mind that it's also distributed to those integers as well. So we have 3 to the negative 2. X to the negative 1 times negative 2 is positive 2. 4 to the negative 2. Y to the negative 1 times negative 2 is also positive 2. Then whenever I see these negatives, I want to think that that ends up becoming the reciprocal. It flips where it is in the fraction. So the 3 squared gets brought to the denominator. The 4 squared stays on the numerator. The other terms stay the same. The x squared and the y squared are simplified as much as they can because I don't know what x and y are. However, 4 squared and 3 squared are small enough numbers that you would be expected to go ahead and just write what that is. If it was something like 2,227 to the second power, probably don't need to write what that is. Here you do. So 4 squared is going to be 16. X squared stays as is. 3 squared is 9 because that means 3 times 3. Y squared stays as is. And that's your final answer. So a lot of times exponents are considered simplified when whenever there's a base, there's just one copy of that base and all of your exponents are positive. Now a lot of these rules tie into how the rules work for logarithms, because remember a logarithm by definition is an inverse exponent, so you would expect their simplification to look very similar. And some of the logarithmic properties you may have just already noticed as we were graphing logs, as we were transforming logs into exponents. For example, we noticed always on all of our graphs that regardless of the base of the log, we had the point 1, 0. So what we actually just knew, if I have log base anything of x equals y, that log base anything of 1 is equal to 0. So that's something that we end up utilizing all the time, because the equivalent exponential form, same base to the output is the input, any base to the 0 is 1, is always true. And then we also always use the point base comma 1 as well for the same reason, that any base to the first power is itself. So if I plug the log base into the log, I'm just going to get 1. And that's used all the time. So even if I have a really funky log, like log base 301 of 1, what is that still going to equal? That will still just equal 0 no matter what. And if you don't have that rule memorized, you can always still convert him to an exponent. So same base 301 to the output, in this case y, is equal to 1. 301 to what power gives me 1? That must be 0. This is where people end up kind of using the term cancel out a little bit willy-nilly at times, but it does actually apply. That you'll oftentimes just see people cross this out. What they're doing is they're crossing it out and saying that this is equal to 1. And let's just remind ourselves on why that is. So log base 301 of 301 is saying 301 to what power gives me itself? 1. Or if you wanted to explicitly write down converting this guy to an exponent, we would do same base 301 to the output y is equal to the input 301, and 301 to the y power is 301, y has to equal 1. And that's what people mean when they cross that out. They're really crossing that out to make 1. And there's a couple of other different ways that we can think of logs quote-unquote canceling out. And we talked about this a little bit in the previous video. If I put an exponent inside my log of the same base, if I have log base b of b to the x, we effectively have canceled that out to be left with just x. But let's actually convert that to see why that is. So this is an example like this first one we have here. So log base 301 of 301 to the 200th power. Let's formally convert this to an exponent to see why this quote-unquote canceling out works. So we do same base 301 to the output y is equal to the input, and the input is that entire phrase, 301 to the 200. So I'm saying 301 to what power gives me 301 to the 200, which is a rather silly thing to say because I just told you the power on 301 was 200. So my answer is 200. A shorthand way, once you get comfortable enough with these that you may end up writing it in the middle of a problem, is you'll see log base 301 of 301 to the 200, and you'll kind of just cancel out the log and the 301 and say that just leaves me with 200. Which, as long as you understand what you're doing there, is fine. You're saying, I know the definition of a log means that my answer has to be 200 here, because I'm saying 301 to what power gives me 301 to the 200? 200. And it works the other way around as well. So if I notice that the base, and I have a log inside the base of the same base, that also sort of cancels out to just leave you with that other number. But let's again kind of go through why that is. So here, if I wanted to convert this to a logarithm, I would have log of the same base 301 of the output, in this case y, is equal to the input, which is this entire phrase is the input because all of it's inside the exponent. Log base 301 of 200. So what I just set up for myself is saying log base 301 of something is equal to log base 301 of 200. So what does that something have to equal? 200. So that's why shorthand, a lot of times, anytime you see logarithms and exponents mixing and their bases match, people just sort of cross it out, say that cancels out, leaves you with whatever's left. That's really what's going on here. So the first type of log rule that we will be exposed to, besides those sort of special cases where they quote-unquote cancel out the log, is the product rule, product being the result of multiplication. And remember that for an exponent, if I have the same base of something being raised to the nth power, same base being raised to the nth power, we end up adding those exponents. And it works very similarly for logs. So in case you're curious, I included math proof here. I'm not going to go through the details of that, but if you want to go through the details more, I'm sure your instructor would be very happy to talk about that during office hours with you if that's something that interests you. The short of it is that just like multiplication and addition are related for exponents, they're related for logs as well. So in particular, if I'm multiplying inside a log, that becomes adding outside a log. Notice how that's sort of the inverse of exponents. For the exponents, if I multiply outside the log, that becomes adding inside the log. for logs, multiplying inside the log becomes adding outside the log. They're inverses of each other. So let's actually practice that. So here for this first one, if I see 8k, remember that's secretly 8 times k. So what does that multiplying inside the log become? It becomes adding outside the log. So in particular, that becomes log base 5 of 8 plus log base 5 of k. So that multiplication inside became adding outside. Go ahead and try this next one yourself, and it's okay if it takes you more than one step to completely break apart this multiplication. So let's talk about this one. So in particular, I might first notice I've got a 30x times the parentheses of 3x plus 4. You may be tempted to distribute this. Don't do that, because if you distribute it, you're going to have just a whole bunch of things being added inside a log, and we have no rules on how to break that up. I can only break up multiplication inside a log, or I can break up division inside a log. So we'll get to division here in a second. We're dealing with multiplication for now. So for this multiplication, what does multiplication inside a log become again? Becomes adding outside a log. So in particular, if I'm just breaking up this part first, that becomes log base 3 of 30x plus log base 3 of 3x plus 4. Then I might notice, oh, 30x, that's kind of like 8k. I can actually break that up more. That really is multiplication. There's just a secret multiplication and symbol in there that we don't actually write. So that becomes further addition outside a log. Log base 3 of 30 plus log base 3 of x plus, and then it might be tempting here, you might say, oh my gosh, I've got another 3x, I can break that up. And if that 3x was by himself, you could, but because that 4 is being added to the 3x, you cannot, because order of operations wise, you have to evaluate this entire thing before you start doing the logs, so there's actually nothing else I can do with that last term. I just rewrite him, and that is all I can do to break up that log using the product rule. For the quotient rule, it looks like there is a slight typo on this slide. I'll be sure to fix that on the version that you get. If I have division outside a log, that becomes subtraction inside a log. So similarly, division, I just said that about logs, and we're talking about exponents. We're pointing to exponents. Let's backtrack that. Division outside an exponent, let's just write that. Division outside an exponent becomes subtraction inside the exponent. So similarly for logs, division inside the log becomes subtraction outside the log. And again, a math proof has been included if you're curious about that. But it should hopefully kind of make intuitive sense that if they are inverses, their rules should be related, and they're just inverted. The inside-outside flipped. So anytime you see division inside a log, you break that up into subtraction outside. So let's go ahead and do that. And if you have a combination of both the product and quotient rule, you sort of treat it like I've got parentheses up here. And order of operations wise, you want to first break up this division, then worry about breaking up stuff inside that parentheses. So let's do that. This division inside a log becomes subtraction outside the log. So I have log base 3 of 4x minus log base 3 of 3. And then I can further simplify this. In particular, 4x, you should be thinking, oh, that's 4 times x. I can break that up further using the product rule into log base 3 of 4 plus log base 3 of x. And anytime you see what's inside the log somehow match the base, alarm bells should be going off that something special is going to be happening. In particular, log base 3 of 3 is saying 3 to what power gives me itself? That's 1. And then you could always do that off to the side if you didn't quite remember that log base 3 of 3 equals y. That becomes same base 3 to the output y is equal to 3. So what does y have to equal? 1. So that equals 1 there. Go ahead and break up this next one yourself and then restart the video whenever you're done. So this division becomes subtraction, so we have the natural log of 10 minus the natural log of 4x plus 1. Natural log is secretly base e, so nothing particularly special happens with the natural log of 10. And as tempting as it might be to try to break up 4x plus 1 further, I cannot. Because of this plus 1, this is just considered one big old term, and there's nothing else that can happen with him. So before we go further, let's continue to practice with the quotient rule and the product rule. What will be a little bit different here is if you notice that anything factors inside the log, I would go ahead and do that factoring first. So let's write that down. So do any factoring inside the log that you can, because that might allow you to either simplify further inside the log or to at least be able to break up more things. So for this first one, this has already been pre-factored for you. And in particular, we want to think about this being a giant parentheses on the top and giant parentheses on the bottom, and we want to deal with this large fraction first. So that will become log base 2 of 15x times x minus 1 minus, because division inside the log becomes subtraction outside the log base 2 of 3x plus 4 times 2 minus x. With whenever you have parentheses next to it like this, that means they're being multiplied. Now let's continue to break this up. So in particular for this first one, I have a 15x times an x minus 1. That multiplication inside the log becomes addition outside the log. So that'll be log base 2 of 15x plus log base 2 of x minus 1. Here, kind of keep in mind this whole thing has a parentheses around it. So as I break up this log base 2 of 3x plus 4 and 2 minus x, keep in mind that whole thing is being subtracted. So I have minus log base 2 of 3x plus 4 plus, because we multiplication inside the log becomes addition outside, log base 2 of 2 minus x. And then we want to further break this up, and we want to deal with this subtraction with parentheses. So 15x, that further breaks up because that's 15 times x. That becomes log base 2 of 15 plus log base 2 of x. X minus 1 can't break up further. I'm just going to rewrite him. Log base 2 of x minus 1. I'm going to distribute the subtraction to both of these terms. Minus log base 2 of 3x plus 4 minus log base 2 of 2 minus x. And that would be my final answer. My log has been completely expanded. For this next problem, it's going to be simplest if you first factor. So in particular, I might notice that my numerator should factor further. So that becomes log base 7 of, what's the greatest common factor between 7x squared and 21x? That would be 7x. Parentheses, 7x squared divided by 7x is going to leave me with 1x. 21x divided by 7x is going to leave me with plus 3. All divided by, we've got this 7x, x minus 1, x minus 2. And before we go on automatic pilot, does anything simplify inside this log? It does. 7x divided by 7x makes 1, so that cancels out, so to speak. Now I'm ready to start expanding this log. I want you to go ahead and pause the video and try to expand this log from here yourself, and then compare with what we get. So this would become, this large division turns into subtraction outside the log. So we have log base 7 of x plus 3 minus log base 7 of x minus 1 times x minus 2. Then you want to break up this multiplication inside this log, and keep in mind that this subtraction will still be attached to the whole thing. So we have log base 7 of x plus 3 minus parentheses log base 7 of x minus 1 plus log base 7 of x minus 2. And then we want to make sure to distribute that subtraction to both. Now, if you trust yourself to go ahead and distribute that subtraction right away as you're pulling out that multiplication to become addition, go for it. This is the way I find myself less prone to error, but you might be a little bit different. So our final answer, that log base 7 x plus 3 doesn't break down further. I'm just continuing to rewrite him. And then we have minus log base 7 of x minus 1, and then minus log base 7 of x minus 2. And now that has been completely expanded. The last rule is the power rule, which is actually just a special case of the product rule. Because remember, if I have something like x to the third power, that literally means I'm multiplying x by itself 3 times. So I could break that up into adding all of those x's. So for example, log x times x becomes log base b of x plus log base b of x plus log base b of x. And repeated addition can be rewritten as multiplication. So that's exactly what this power rule says, is if I have anything to some power inside a log, I can pull that power out front of the log to become that power times the log. And this is actually the most powerful rule that we have, pun intended, because we end up using it all the time. Every single time we're solving a whole bunch of log and exponential equations, we end up exploiting this rule a lot. So the more familiar you can get with this rule, the better off you will be. So let's look at some examples of this. So if you have log base 2 of x to the 5th, that means I can pull that 5 right out front, and that becomes 5 log base 2 of x. What about this next one? Go ahead and pause the video and try that yourself. That means I can pull the 2 out front, and that becomes 2 natural log of x. When it comes to expanding logarithms, let's just get ourselves a nice order that we can follow each time. So the first thing you want to do is deal with any large fractions. First, want to break that up. Then you want to deal with breaking apart multiplication. Then you want to deal with the power rule at the end. Power rule should always be the last step you deal with, really. And this is kind of a general order. It might depend slightly based on the context where maybe some parentheses have been placed, but this is a general order that will work. So first here we have this large fraction. Let's break that up. And fractions are the same thing as division. So what does this division become outside the log? It becomes subtraction. So then we have natural log of the square root of x to the third plus 5 times y, if you sort of notice that y is outside the square root, minus the natural log of 7x. So I've dealt with my large fraction there. Now I want to start breaking apart the multiplication. So in particular for this first term, I can break apart this multiplication inside the log to some addition outside the log. So I have the natural log of the square root of x cubed plus 5 plus the natural log of y, and then minus, and then this whole thing in parentheses, 7x. Don't forget to break apart. This is actually multiplication here. Natural log of 7 plus the natural log of x. Now I'm going to notice that a square root I can actually rewrite as a power. What power is that? That would be to the 1/2 power. So I have x cubed plus 5 all to the 1/2 power. We still have that natural log of y, and then I'm going to go ahead and distribute that subtraction to both terms. Some people just distribute that right away. They just go ahead and notice that since I'm minusing the natural log, when I break that up to be addition, that will actually turn to subtraction. Either way you want to think about that is completely fine, as long as this is your final result, that both of those are really being subtracted because they both came from my denominator. Now I want to deal with my last rule, which is the power rule, and that says that this 1/2 is going to move out front. So we have 1/2 the natural log of x cubed plus 5. That doesn't break up any further because I have that plus 5 there, plus the natural log of y, minus the natural log of 7, minus the natural log of x, and that is my fully expanded logarithm. Go ahead and pause this video and try this one yourself. Keep in mind that that denominator does factor, so don't forget to factor that denominator. All right, let's go ahead and go over this. So here, I'm going to go ahead and first write factoring that denominator. And I'm going to go ahead and rewrite this cube root is the same as what power? That is the 1/3 power. So I'm actually going to go ahead and write that as well. So we have x minus 2 times x plus 5 squared all to the 1/3 power over x minus 1 times x plus 1. So don't get overwhelmed, take it one step at a time. Do I have a big giant fraction I can break apart? I do. Let's go ahead and break that up. So this big giant fraction inside the log, which is division inside the log, becomes subtraction outside the log. So let's do that first. So we have log of, and then we have this big old term. It looks like we've got x minus 2 times x plus 5 squared, all to the 1/3 power, all inside that first log, minus log of x minus 1 times x plus 1. We've dealt with the big old fraction. Now, this is a case where that order I told you, you have to think about order of operations a little bit more. Since this entire thing is being taken to the 1/3 power, that's sort of the outside power, and for this outside power, there's nothing else being further multiplied. So I do want to deal with this power first. I want to go ahead and move this 1/3 out front first. Or you could think of, if you don't like doing that, you could instead distribute that 1/3 to each of these terms in the middle. Either way is a completely fine step to do this next step. I am personally going to actually move the 1/3 out front because I find that a little bit less messy, but you could do it either way. So that becomes 1/3 log of x minus 2 times x plus 5 squared, minus parentheses, and then this multiplication inside the log still becomes addition outside the log. So log of x minus 1 plus log of x plus 1. Now I want to continue to break up this log. So here I've got two things being multiplied still inside this log, which will become addition outside the log. And this 1/3 is a coefficient on this log now, so he's going to follow the whole time. So we have 1/3 log of x minus 2 plus 1/3. Oh, I said 1/3 and then I forgot to write it, of course. 1/3 log of x plus 5 squared. And then I'm going to also distribute that subtraction to both of these terms, minus log of x minus 1 minus log of x plus 1. We're almost there. We have one more thing that we can do. Are you able to spot that? This squared inside this log still becomes multiplication outside the log. And we're just going to go ahead and multiply that 2 to that 1/3. And 2 times 1/3 gets us 2/3. So our final answer is we have 1/3 log of x minus 2 plus 2/3 log of x plus 5 minus log of x minus 1 minus log of x plus 1. And if you have completely expanded it, there should be no more powers inside the log, nothing else being multiplied inside the log, nothing else being divided inside the log. Only operation that should be going on inside your log should be addition and subtraction. And that's exactly what we have here. We also could work the other way around, and actually working the other way around is a little bit more common and is a little bit more helpful usually for solving problems. And we're going to be doing that in the reverse order that we did our previous problems. So first we're going to apply the power property, then we're going to work with the product and quotient properties. So first you're going to notice any numbers outside the log are going to move inside the log into an exponent. Then you're going to start converting that addition subtraction into multiplication division. So let's see that in practice. So for both of these, are there any power rules that I have to apply? There are not, because there's no numbers chilling outside any of these logs. So we're just going to be dealing with addition becoming multiplication, subtraction becoming division, and we're just going to move left to right in terms of that. So first I'm going to notice here, was the addition outside the log become again? That becomes multiplication inside the log. So I have log base 3 of 10 times 2 minus log base 3 of 4. And then I'm just going to keep on going. What does the subtraction outside the log become? That becomes division. So that becomes 10 times 2 all over 4. And then I'm going to actually simplify inside this log. So 10 times 2 gets me 20, divided by 4 gets me 5. My final answer is log base 3 of 5. Go ahead and try this next one yourself. It's okay if at the end we are left with a fraction inside the log. Fractions are just numbers, don't freak out. All right, let's go ahead and start doing this. So I would just move left to right. It's not the only way you could do this, but I find it least prone to error. First thing I'll notice is the subtraction outside the log becomes division inside the log. And then I'm just going to drop down my other terms. And then I'm going to keep on going. So this addition outside the log becomes multiplication inside the log. Keep in mind 4 is currently over 1 at the moment, so that becomes natural log of 6 times 4 over 7. And then we've got minus natural log of 2. And then this subtraction outside the log becomes division inside, which that means that 2 moves into the denominator. So we have 6 times 4 over 7 times 2. If we want to simplify this a little bit, 4 divided by 2 gives me 2. So that becomes the natural log of 6 times 2 is 12 over 7 as your final answer. Now let's deal with a case where we have a little bit more going on the logarithm. So first thing we do need to make sure we deal with here is any case where we can employ the power rule. So for this very first term, it looks like the power rule has actually already been applied. I already have a y to the third inside, and then we've got nothing on the outside. So I'm just going to rewrite him for now. For this next one, this 1/2 on the outside moves to the inside. So that becomes log base 7 of x plus 3 all to the 1/2 power. Then for the next one, this 10 is going to move to the inside. Notice I haven't touched the addition subtraction at all yet. I'm just dealing with one step at a time. So that's log base 7 of x minus 2 squared all to the 10th power. And now let's just actually simplify that a little bit. If I have x minus 2 squared all to the 10th power, that makes 2 times 10 gives us 20. So that's log base 7 of x minus 2 to the 20th. You also could optionally rewrite this 1/2 as a square root if you wanted. I would just pay attention to directions on if they want you to keep it as a half or if they want you to keep it as a root. I'm just going to keep it as a half for now. Now you want to start doing the exact same process we did earlier of combining addition, subtraction, just left to right. So first let's deal with these two terms. So this addition outside the log becomes multiplication inside the log. So that becomes log base 7 of y to the third times x plus 3 to the 1/2, making sure that you make it clear that 1/2 is just attached to the x plus 3 and that third is just attached to the y. And I'm just going to rewrite the other term. Now you're ready to go ahead and combine these. So that subtraction outside the log becomes division inside the log. So that's y to the third times x plus 3 to the 1/2 all over x minus 2 to the 20th. And then you'd be done. If you really want to rewrite this x plus 3 to the 1/2 as the square root of x plus 3, go crazy. Otherwise, you are good. Go ahead and pause this video and try this next one yourself. Don't be thrown off by a fraction being here. That's fine. Just kind of follow where he goes. He's just a number. All right, let's go ahead and go through this. So the first thing you want to do is make sure that you move any numbers on the outside of the log into those exponents. So we have log base 2 of y to the third minus log base 2 of y, and that's a really messy y. Ooh, drawing on a computer sometimes. Okay. Y minus 2 squared plus log base 2 of 6y minus 3 all to the 1 over y. Now we're ready to start combining these left to right. So left to right, first things first, these guys. We have log base 2 of y to the third all over y minus 2 squared. And then we've got plus log base 2 of 6y minus 3 all to the 1 over y. Then we just keep on combining, and whenever we're combining this, addition becomes multiplication. And multiplying this is really over 1 right now, so this will be multiplied into that numerator. So we have as our final answer log base 2 of y to the third times 6y minus 3 to the 1 over y all over y minus 2 squared. And that would be our final answer. You also could change that 1 over y to the white root of 6y minus 3 if you wanted to. Just pay attention to directions if they want you to keep it as an exponent or turn it into a root. The last one is the change of base formula. To be honest, this is not one that we emphasize as much in this class since modern calculators can really use any base of logs. This is most helpful if you want to get a decimal approximation of something and are using an old-fashioned calculator that can only do traditional bases like base E and base 10. And the short of it is if you have whatever favorite base you want to change this log into, if you do log of the input over log of the base, you can convert it. So if, for example, I wanted to find log base 7 of 2, that would be the same thing as log base 7, or no, I was about to keep the same base. Yeah. That'd be like log base 10, something that's easy to put on a calculator. Log base 10 of 2 over log base 10 of 7, which would be the same thing as the natural log of 2 divided by the natural log of 7.
Hello.
Whatever it is that you might be wanting to work with there. So change of base formula is used most often to get log or natural log. So for example, if I want to find log base 5 of 3, and we want to rewrite natural logarithms, that would be the natural log of 3 divided by the natural log of 5. And the reason why you end up doing that is because a lot of times you then want to use your calculator to find approximations. So let's take a look at an example of that. So this type of calculator, you actually can just directly type in log base 5 of 3, which is kind of nice. Or you could type in, if you're using a more traditional calculator, natural log of 3 divided by natural log of 5 will get you the same answer. Or you could do log base 10, that's log without anything written, and that will again get you the same answer. So that's where it's used most often, is if you're using a traditional calculator. Or let's say you're wanting to combine logs and they currently were written in different bases and you just wanted to rewrite them all in terms of the same base for some reason. Same idea here. So if you have log base 1/2 of 8, you can rewrite that as well. That would just be log base 10, with base 10 being what you don't tend to actually physically write, of 8 over log of 0.5. And again, you can always double check that with any sort of calculator. So if for this case we had log base 0.5 of 8, we could put in 8 there and put in 0.5 there. That would get you that same answer of -3. Or you put that there too, and that will get you -3 as well. As always, please be sure to check out your textbook if you want even more examples, or talk to your professor as well. That's why they're there. Please ask all the questions that you need. Logs can be a little bit tricky at first for some folks if you're not used to thinking about things in terms of logs, but really emphasize to yourself that it is an inverse of an exponent. Therefore, those log rules are just the inverse of those exponent rules. So multiplication is related to addition, subtraction is related to division. And have a great time mathing.